Okay, so this is going to be the second part of this video series where I walk through developing your own ESP32 board. And in this part, I'm going to go through part selection and building the schematic. So I've got a brand new project set up in Kicad. It's blank. We're starting from nothing. And so here we go. Now, as it turns out, the very first thing we need to do is not to just start whacking stuff into Kicad. We actually need to make sure that we have the right parts selected. That way we can ensure that we have the correct symbols and footprints and everything else we need going forward in Kicad. So I've generically listed the parts that I need, and now I'm going to go out and I'm going to find the specific parts and get whatever I need as far as symbols and stuff before I start laying down the schematic. So I'm going to be using JLC PCB to make my boards and do the board assembly, and so while I'm selecting parts, I'm going to make sure that I pick parts that JLC has that are in stock, and I'm going to document what part numbers they are, because when I go to do my ordering, this will just make that easier. So if you're using a different board house, you might be ordering parts and this may not be as important, but I want everything to work smoothly, and so I'm going to do this as part of that process. Okay, so the first thing is, what ESP32 chip am I going to use? And I'm going to use the C3, and so I'm going to go find the exact ESP32 C3 module that I'm going to be using. And so I'm out on JLC's website, and this is where you can look up what parts they have. I'm going to do, spell it correctly, ESP32C3. Okay, and if I come down here, I'm going to sort by price because I want the cheapest version basically possible. And this is where you got to be careful because they do have bare chips, but I don't want the bare chip. I want a module. And so here you can see that they have the U4. So this is going to be, if I mouse over, you can see the image. This does not have the onboard antenna, and that's what I want. I want the onboard antenna. And so the cheapest version of that they have is the ESP32C3 Mini H4. And looking around, this does seem like it's going to be the best choice. I do want the mini version. It's going to be a little smaller. This thing costs about $2.10 a pop. They do have like the N4 and then the H4X. These are just small variations that are like different heat tolerances. And I believe the X model is actually just a slightly newer version of the IC. So basically, Espressif has updated the chip a little bit, but that's not important for this. So I'm going to use this particular part number, and so I'm just going to copy that. And then I'm going to go make sure that I have the symbol, footprint, and 3D model for this chip. Now, one nice thing is that Espressif actually has a GitHub with libraries already built. And so if I click out here, I just web search for ESP32 footprints, you'll see the Espressif Kicad libraries. And so this has footprints, it's got 3D models, and so it's going to have symbols and all kinds of stuff. So if I click into symbols, this is the first thing I need, and so I'm just going to download this raw file. And so I'm going to save this in a folder in this project folder for my Kicad project. And so I'm going to create a little folder called resources, and I'm just going to save this there. And this is where I'm going to drop everything. That way I can always easily go find all my symbols and footprints and 3D models and everything else I need all in one little place contained for this project. Okay, so I'm also going to grab the footprint. This is going to be the physical footprint for whenever the PCB gets assembled. Hey, what shape do the pins have and things like this. And then the last thing is the 3D model. And so now I've got my ESP32 and I have the symbol, footprint, and the 3D model. Okay, so the next thing we need is a USB connector. Now I have some experience doing these boards, and so the USB connector that I'm going to use is a generic part. Now, what it's based on is this Amphenol connector. This, and again, it's super long number, but you can see it right here. It is a pretty decent little USB-C connector, and as you can see, it's small. And the thing is that I have already double-checked what I'm about to show you. There are generic versions of this that are basically perfectly compatible. And the specific version I'm going to be using is this G-switch, GT USB, blah, 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 blah. This is basically a complete clone of that Amphenol part, except for, it cost 8 cents, whereas the official one costs 60 cents, and it's just a USB connector. And again, I've already done this before, and I know. Now, just to show you, like, again, things I've done in the past, just to show you how this kind of works, this is the drawing of the Amphenol part. And so the things that you really want to be careful with are the footprint, and you want to check all the dimensions on this thing, the spacings, the pin size, and everything. So as you know, I was looking at this part and it looks visually, similar. I started looking at, okay, this thing is 7.35 millimeters long by 8.94 wide. And then if I look at the G switch version, you'll see over here it is 7.35 millimeters long. And the width is a little trickier to come by, but over here you'll see that it is like 8.64, but that's center to center. And if you add another 0.3 for the width, that's going to be 8.94 wide. The mounting lugs are in the same spots. You see like the center to center on the mounting lugs here, 5.78 for these little pins that come out the bottom. And over here on the G switch version, 5.78. And so again, I went through and I verified all the spacings, and I know these two parts physically have the exact same dimensions. And so this is why I'm going to use it as a replacement, because it's much cheaper and it is quite clearly the same physical dimensions. It's going to fit on the footprint. It's going to be the same size as far as everything. So again, I just wanted to cover that because you have to do this anytime you want to use a substitute knockoff part. You have to make sure that it really is going to fit correctly, especially with USB-C connectors, because the pin spacings are so close and the mounting and everything has such high tolerances that if it's off a little bit, this thing isn't going to work. And so you really do have to check that stuff on your footprints before you start just swapping parts. Just because they look the same doesn't mean they're actually the same. So now that I've done that, I'm out on the Amphenol website, and if I scroll down, it'll show, hey, here's the symbol, the footprint, the 3D model, powered by Snapmagic. So I'm going to download all of this stuff. And now I've got my footprint, and I've got the step file for the 3D, I've got the symbol and everything here. Okay, so I am going to go ahead and get all this stuff filled out. I'll come back and show you what I picked, and essentially it's the same process for the rest of these parts. I just don't want to make this video too dang boring. I know it's already a little dry starting off, but I'll go ahead and get all this stuff set up. Now, one thing I thought about while I was out here selecting parts, that if you've never done this, it's just something you kind of pick up along the way. Whenever you're looking for a part, you do want to start off thinking about what your assembly or suppliers have in stock, right? You don't want to pick parts that have really low stock values that they can't get a hold of, because that can just slow down the whole ordering thing. And often you know kind of what parameters of a part you need. Like, so if it's a voltage regulator, you know, like, okay, here's what voltage input I'm going to have, here's what voltage output I need, and here's how much current I need, right? And so, since I'm using JLC, you can come out and search their parts to see what they have, but there's some hiccups there because JLC's part search kind of stinks. It's gotten better over time. It used to be real bad, but it's not always super handy. And so when you're out here looking, you can have a lot of frustrations with the way their search and filters work on their search. The other thing is when you actually do get a part, you might get out there and find out that the data sheet that JLC has in their parts library is all in Chinese. And now look, translation's gotten pretty good these days, built into web browsers and stuff, but sometimes it's still like, man, I need a non-translate, I need an English data sheet. And so what you can do, there's some other ways to go about this. So number one, JLC PCB has a sister company. Basically, they're both owned by the same parent company called LCSC Electronics, and its website has much better kind of search features. And the nice thing about that is if you find something on LCSC, it's almost always available at JLC PCB. Now, not 100% of the time, but most of the time. And what you can do is if you go out and you find a part on LCSC, you can actually pull that part up in their system and the part number. In LCSC, if you copy that and you go into JLC PCB and you search for it, what you find out is that they actually use the same part numbers. And so you can actually verify, does JLC PCB have this part, by just checking these numbers, and most of the time they do. The nice thing about that is, again, the LCSC website's just a little easier to use to find parts. Now, it doesn't fix the kind of, data sheets being in Chinese, because usually, again, JLC PCB's kind of pulling in LCSC stuff, so that's really not going to be fixed. So the other thing I often do is I'll use like DigiKey or Mouser to actually search for parts, and they have very good search systems, and all the PDFs for all the data sheets are usually going to be in English. And so that means that I can usually find a part on DigiKey or Mouser, but since I'm going to be using JLC PCB for assembly, I want to make sure that they have the part. So I'll first do some searching in DigiKey, Mouser, and then I'll go over and search for that part on JLC PCB to verify they have stock. And that's another way that I go kind of back and forth figuring out what parts I want to use. So this is also kind of related to finding footprints, because if I want to find a footprint, on a certain part, JLC PCB and LCSC will provide footprints and symbols, and sometimes even 3D models. But there's a problem here, is that it goes through Easy EDA, and that requires like an account, and it's not always easy to get stuff out of Easy EDA. So another source of footprints and symbols and 3D models and stuff like that, you start to learn that there are just other sources for stuff. So once again, this is what's useful. Like DigiKey and Mouser sometimes will provide EDA models. And so with DigiKey, like this stuff usually comes out of like Snap EDA. And so that's one source. So you don't have to go through DigiKey to get this stuff, but you can see they provide links to Ultra Librarian and Snap Magic, which is again Snap EDA. And so if you get Ultra Librarian and Snap EDA accounts, you can often get a ton of footprints from those online resources for stuff that can otherwise be somewhat hard to find and may not be included in Kicad. Now, Espressif provides all footprints and everything for their stuff, but other parts you may have some difficulty. Sometimes the manufacturer will have footprints and 3D models and stuff available, but again, if you go through those resources, you don't find anything. Again, check Ultra Librarian and Snap Magic, because again, they will have a lot of stuff, and sometimes it's even user contributions. You'll find footprints for stuff built. So, obviously you can always build your own, but man, that takes a lot of time. The only hiccup with that is you always want to verify your footprints and symbols and stuff that actually matches the exact part that you're using, because you don't want to go through your whole layout and then find out, oops, my footprint had an error. That's happened to me before because I was lazy and sloppy, but again, things to think about when you're going through this process. Okay, so I have collected all the symbols, footprints, and models for all the special parts that I'm going to be using. Now look, I don't do this for resistors and capacitors and stuff like that. That's very, very normal, but all the specialized parts I want to collect. And so here you can see what I've got going. I've got the USB connectors, I've got voltage regulators, I've got, my battery charger chip, the jacks I'm going to be using for connectors, the connector for the battery, a couple of specialty diodes for the USB and ESD protection, a little switch to control for like boot and reset, and then a little power mux, and this is basically going to switch between USB and battery power depending on what's available. So I've also recorded all the JLC parts, and so I will have all this referenced in the future. Now, as I've been adding this to my little custom folders, you can see it's now been populated into this project that I'm working on. And so you can see I've got all these different footprints and all these different symbols. And so I'll be able to add these in to the schematic now. So if I open up the schematic editor, I'm now going to go to Preferences and Manage Symbol Libraries. So I'm going to add a custom library. So I'm just going to navigate to the folder where I put all that stuff. And here's my resources and now symbols. And now I see all those symbols. So I can select all those, hit open, hit OK. And now it's going to update. Now I'll have all those available in my schematic. Now later I'll add in the footprints, and that'll be whenever we go to start doing the PCB layout. All right, so I'm going to start placing components. And so once I open up my symbols, start typing ESP32, C3, And I should see right here the mini dash one. It says footprint not found, but that's because, again, I haven't associated any footprint with it yet. So there is my symbol. And so I'm going to add my major parts right off the bat. So there's my USB, my voltage regulator, my battery charger, power mux, battery connector, one of my diodes, the other diode, switch, and there's our jack. So we got our major components, and now we can start building the schematic. Now that we've got all the main footprints, now all we got to worry about is just other kind of passive components with very standardized footprints. So the first thing we're going to do is get the ESP32 all wired in. So we want to add some power pins. So I'm going to place power symbols. So we want 3.3 volts. We want a ground. All right, the next thing we need to do is make sure that our enable pin, that's going to be the boot, and then our reset pin are both wired in with buttons. That way we can get this thing to be programmed and everything kind of works the way it's supposed to during boot. It's got our little switch over here that we're going to be using. Okay, so now I can get rid of this, take this other switch, pop it down here. Now we're essentially just going to duplicate actually this whole piece over here, and this is going to be for the reset button. And GPO 9, this is going to be the reset button. So now we've got our boot and reset buttons set up, and I'll assign the specific parts later on these. One thing that I want to do is to make sure that I don't use any strapping pins that I don't need to, and that means that I don't want to use GPIO 2 or GPIO 8 because those are going to be strapping pins. So I'm just going to hit Q, and that's going to allow me to say don't use these. So those will just be left unconnected, and I won't get those mixed up later whenever I'm trying to do things that, again, gets me into weird boot problems. That's the basics here. The other thing I need to do is let's go ahead and add the USB. Okay, so I'm going to place a global label here, and I'm going to put that on USB plus. Then I'm going to copy it, and this one is going to be USB minus. So now I've got these pins labeled, and now I can move on to other stuff for now. So let's get the, while we're here, get the USB set up. So immediately we need to connect these, and let's place them. Let's flip them over. So now we'll have data minus to the USB minus, data plus to the USB plus. Okay, so VBus, this is going to be power. So 5 volts in is going to come out right here. I'm just going to call it VBus. Doesn't really matter. You don't have to use these symbols, but I'm just going to call it VBus. All right, so that's where this little special diode is. So this is just going to be a little bit of like a transient voltage suppression, like a ESD suppression. So that's all this is really for. And then we also need, actually I'm going to have to draw these out a little bit because this is for our other diodes. So once again, I'm going to change these footprints out to just something that makes a little bit more sense just in the schematic. I'm going to use one of these. And it's a very similar kind of diode. It's just not nearly as big. And so again, it just doesn't take nearly as much space. So again, this is just to protect the data lines. And now we need a ground pin. Okay, so this SBU2 and SBU1, those are shield, and those don't need to be connected to anything. There we go. So those won't be connected. The shield won't be connected to anything. What do I got left? I need to connect these data pins over here. And so for this, I'm going to use little net labels. It's going to do D underscore P and D underscore N. And so that's going to be data positive, data negative. And I put that one on the wrong lines. Let's again, net labels, this one D underscore N, D positive. So these will now map in and they'll be connected over here to these USB pins, just so everything ties together. Let's see, what else? I've got the CC1 A and B. So these two need 5.1K resistors for like power to work right. And that resistor is going to be going to ground. And again, that's going to come all the way and go to ground. And that's actually where the rest of this stuff goes. I think I said that this was shield and I'm wrong. Here are the shield pins. They all need to be connected to ground, as do the ground pins. And so, yeah, I misspoke. These SBU1, SBU2, those are like some sideband communication thing. That's what the SB is, not shield. But they're unnecessary, so we're just going to leave those unconnected. And that is basically the USB connector, except I missed this ground over here. So ground, ground. So the big important pieces, right? Your USB needs to be connected to the data pins. You've got the protection diodes, one for each data line. We've got the reverse voltage suppression here. This is kind of a TVS diode. And then the 5.1K resistors, those values are important, both coming from your CC pins to ground, making sure your data lines are all connected together. And so that is a basic USB-C connector. Next up, the voltage regulator. So once again, going to go to the data sheet, look at the recommended application schematic, and see what we need to do with this one. Okay, so the voltage regulator I'm using is a switching buck converter, and so it requires a bit more in the way of components. You'll see that it needs an inductor, it's got a few capacitors, it's got here a little resistor network that sets the feedback. This little C3 has an asterisk, and I've used these before, so I know that that's a feed-forward capacitor that might be necessary for stability. We've got a power good signal, and this is basically it can send a signal to a microcontroller, just tell it everything's fine. So it's got a 4.7 microfarad coming in and a 22 microfarad on the output. So Vin goes to enable. All right, and then that comes in from, let's see, this is going to come in from our VN. This is going to be the system voltage bus. Could be battery voltage, could be USB. And then this is going to be our 3.3 on the output, but I need to double check because these resistors, it's adjustable. Okay, so here are some of the important specs for this one. It says, look, output voltage is set by an external resistor divider according to equation 2, which here it is. And it gives us R1 in terms of R2. So R2 times V out divided by 0.6 volts. Okay, so that means that if I want my V out to be 3.3 volts divided by 0.6 volts minus 1, so this means that R1 needs to be 4.5 times as big as R2. And it says R2 must be less than 100 kiloohms or 100,000 ohms to provide acceptable noise sensitivity, which means if I use a 100K for R2, that would mean I need to be like 450 for R1. And so this is where, again, we want to go look for, hey, what resistor values are common, and try to find two resistor values that are, a multiple of 4.5 times the other. And so looking through all that, turned up that the best values are probably going to be 100K on the bottom and then a 453K on the top. And that will be a ratio of 4.53, and I was looking for 4.5, and that's about as good as I can do. If I start pulling this resistor down, it actually widened the ratio a little bit, so this is about as close as I can get to 4.5. So next up on the output capacitors, it says if my voltage is above 1.8 volts, that there's a double plus on the 22 microfarad outputs is note 3. This is the standard value and recommended for most applications. So that means, inductor of 1 microhenry with output capacitor of 22 microfarads. So back to the reference schematic, this C2 is going to be 22 microfarads, and this is going to be a 1 microhenry on the output. So again, R1, I'm using 453, R2, I'm using 100 in my schematic. Okay, I'm swapping footprints. It turns out Kicad actually has a better footprint than what I got going. So I'm just going to chuck this one. I'm going to rename this U2. And just a better layout on the footprint that just kind of makes more sense the way this thing's arranged. I've had issues before with a little bit of noise coming out of one of these, so I am going to put in this little feed-forward capacitor. Okay, so here I'm just going to make a little note. Let's put some text that these need to be precision resistors for this divider, simply because I really need these to be accurate to set the voltage correctly, because this is going to be setting that 3.3 voltage. This needs to be 1 microhenry. And it also needs to be rated for at least an amp on the output, just to make sure we get enough power on that. And actually, I guess I need to rename this thing. That was not 3.3. That's got to be plus 3.3 volts to match my schematic. There we go. Everything's got to be named correctly so that it matches up. So there we go. And that's the basics. What else do we need? That's going to be the battery. And then we've got audio jacks. All right, it's been a couple days. I got a little swamped with work, so I got to finish up this schematic. And what do I got left? Got the jacks, and I have the power connector. So I'm going to do the power connector next. Let's move it here in the middle to work with it. So now this is just a 2-pin connector. So whichever one you want can be the plus side or the ground side. And what I'll probably do is I'm just going to put this for right now as VBAT on pin 1. But whenever I go to lay this thing out, I may come back in here and swap the pins if I need to, just depending on layout considerations, or if you're using a battery that already has a plug on it and you want to match that, all you have to do is just swap these pins. So that goes right there. And then the other thing I need to do is I want some monitoring on the battery voltage. So I need to put in a voltage divider and then hook this up to an ADC pin on the MCU so I can read voltages. I'm going to be using some fairly high resistor values basically because I don't want to drain the battery too much, and whenever you use a voltage divider on the battery, and so here's going to be the final circuit that I've got here. You'll see what I mean is that if these resistors have too low of a value, it's just going to drain the battery to ground constantly, and that's going to just drain your battery. So I've provided a very high set of resistor values. That way the battery doesn't drain that fast. So just as some quick math here, if we have a battery that's fully charged at 4.2 volts and we provide 4.3 million ohms to ground, you can see that's roughly 1 microamp of current being drawn, which that's not that much compared to what the rest of the circuit's going to do whenever this thing's in deep sleep. So that's the upside of using larger resistor values. The downside is whenever your ADC goes to read right here at this node, it's going to create kind of an instantaneous current draw. And the high impedance here, because these large resistor values, can cause some problems with the ADC read not being able to pull enough current to get a good read. And so that's what this capacitor serves as a bit of a charge reservoir. Whenever that ADC pulls, that this thing will be able to feed some current very quickly, so we get good kind of battery readings. So the reason I'm using mismatched resistors here is also, the bigger resistor on the bottom and the smaller on the top basically puts the actual voltage here at a higher level. And one thing about like a LiPo is it's fully charged at like 4.2 volts. And then in this circuit, it's going to be like fully discharged by like 3.4 volts. So there's not really that big of a range of readings. And if you use like a 50-50 voltage divider, that's going to drop the voltage for the ADC. And that actually limits your use of the full ADC range. And so kind of using this divider array so that it pushes the voltage up allows your ADC to have a wider range of values that it can use, essentially. All right, so I was about to move on to the jacks, but I actually need to put the bat sense pin. And so here's where I need to use an ADC pin. And so you'll see it's helpful on the schematic on this symbol. It does have the ADC pin. So I'm going to put one on here. Now, I will probably come back later and, put this on a different pin. I'm just going to put it on a pin right now. And then probably whenever I do the PCB layout, I may have to move this because one thing to pay attention to is the physical orientation of your pins. That way you don't have to do too much crossing and, trying to do vias and all kinds of stuff. Just not necessary if you do good pin utilization. So just going to put it on a pin right now and then we'll come back. All right. So audio jack. So I guess I'm going to do 4. All right, so in laying these out, essentially what happens is there's going to be a thermistor plugged into this, right? And I'm using 100K thermistors, and so the ADC read is going to come out right here on this pin for each one of these. And then I need another resistor down to the bottom, which means essentially the thermistor is a resistor between these two pins. And so the ADC, once again, it's reading a voltage divider, but the thermistor varies on temperature, and so the voltage at this point varies based on temperature. And whenever you select the bottom side resistor, typically the best way to do it is to pick a value such that in the normal range you need to be measuring, you kind of end up matching what the thermistor is going to be, and that puts it in the midpoint of the range, gives you the best linearity in your readings. And given my resistor values, that means I'm going to be using 750K resistors on the bottom. And you could also put some capacitors in parallel to stabilize this, but I don't think my reads are going to be happening fast enough for that to matter at all. So I'm just going to put these in, and then these will all go to ground. And then I'm going to put, this is going to be our little read flags for the ADC. And then I've got the input, and this is just going to be a high side voltage for all of these. So they're all going to be connected to the same high side voltage. And then I'm just going to read this down here. So the way I'm going to do this is I'm going to use a separate pin to drive the high side. And so I'm just going to call this the NTC power pin. And so basically, if I just take a GPIO and raise it high, that's going to provide plenty of current here because, again, you look at these resistor values and each one of these is going to be doubled because of the thermistor. So you're looking at like 4 1.5 mega ohm resistors in parallel, which means that's going to be like 375K resistance on this thing, and at 3.3 volts. You're looking at 9 milliamps, and so that's just not going to be anything of a stress on a GPIO pin. So that's how I'm going to power this, and what that allows me to do is whenever the device is in deep sleep, the thermistors aren't going to draw any current. I'll just turn them on whenever it wakes up, and that's kind of how I minimize power on a battery-powered device. I make sure that the battery sense voltage divider is very high value so that it doesn't draw much current. And I try to minimize current draw and everything else by hopefully turning things off that don't need to be on whenever you're in deep sleep. So the current draws that we will have kind of no matter what, they're going to be things like, the MCU has an RTC clock and that's going to draw some current in deep sleep. You're going to have some power losses from, your other chips here. So like, if you're on battery, you're still going to be running the voltage regulator. The battery charging chip is still going to have some power, probably a little bit of draw, keeping it like monitoring the battery. And again, any other kind of resistor that's on a power rail that's tied to ground and isn't turned off is going to draw power. So try to minimize that stuff. That's the basic layout though. So this is my kind of initial circuit that I can work from going to my PCB layout. And again, just a quick recap, we've got the MCU, we've got buttons for the boot and reset, and I have just realized that I've got those mislabeled. This is actually the boot button, and this up here is the reset button. So yeah, I mean, mistakes happen. So I've got my boot and reset buttons here. I've got the power routed in. I've got the USB all, tied in. What else do I have on left? Okay, so I've got bat sense. I did not tie in my thermistors, so I need to do that. And once again, I'm just going to put these on ADC pins, and I'll come back during the PCB layout and probably rearrange them just for a little bit of a better physical orientation. Just because, again, as you lay the thing out, you might find that certain pins are just more convenient for routing for other things. So I've got all those tied in. I need an NTC power pin. Okay, let's see, any other things unconnected? I think that's probably good. Looking at everything, I think everything's tied together correctly. And so I'm gonna just get rid of any unconnected pins. Mark them all off that way, otherwise it will bug you. And then we're going to come up here and we're just going to do a little electrical rules checker and just see if anything's unconnected that I didn't see. but I'm mostly just looking to see if anything is not connected, and that looks fine. So the last thing before I move on is sometimes you just look through and if you want to relabel anything, this is a good time to do it. I think everything's mostly fine. You could come back in here and rename like these is like, because these little numbers in Kicad, that's what's going to show up on the PCB labels. So, if I don't want to name this stuff, J, because that's jumper, if I want to name it something different, this is what I would do. So like up here, instead of J1, I could call this USB1. All right, so those jacks are going to have that label, and then like here for the U1, you could call that MCU. This, again, it's just how you could name stuff if you really needed to, but it's not super important if you do that. So I think that's a good place to stop for now. We've got our schematic, and from here, the next step is to start routing the PCB, and so that will be the next video. We'll be doing the PCB layout, and maybe we'll even get to the ordering step at that point. So if you've got any questions or feedback here, feel free to leave them down below. I've tried to make this concise, so I didn't do a ton of, hey, here's how you do this stuff in Kicad. It's not a Kicad tutorial, but this is how I go about laying stuff out and the thought process behind it. So as always, if you got any feedback, comments, or suggestions, feel free to leave them down below. Thanks.